Here we present the solution to problem 4, which appeared on exam 3 in fall 2014. Admittedly, this was probably the trickiest problem on the exam the students had the most trouble with. The problem statement reads, the pin members 1 and 2 of the truss subassemblage below are made from steel W10 by 33 sections. And we give you all the cross-section properties you need, the area, the weak axis I, the radius of gyration, the modulus of elasticity, and the yield stress, 42 ksi. Problem statement reads, determine the allowable axial force F allowable in members 1 and 2, considering the possibility of both yielding and buckling. Note that buckling only occurs in compression members, and apply a factor of safety equal to 2. The second part of the problem, based on an appropriate static analysis, find the allowable load P at joint B. Hint, draw a free body diagram of joint B. So you can recognize, starting out, that there's a distinct separation between point A and point B. Point A is simply a buckling analysis of a single member or yield analysis, and we don't need to do any statics or analysis of the truss itself in order to solve part A. So we'll approach that part first. We can observe actually that both members are going to be compression members. The force downward is going to cause compression in 1 and 2 in order to satisfy equilibrium. So both are going to be in compression. We need to consider buckling for both, and they're the same length. Basically, in terms of the allowable stress, allowable force, it will be the same in members 1 and 2. There's two different approaches we could take to solve part A. We could use a force-based approach. Calculate allowable forces. If we do that, let's start with yield. The yield force, F sub y, is equal to the yield stress, sigma y, times A. Given as 42 ksi for yield stress, an area 8.8 inches squared. That computes to 369.6 kips. The allowable force should be F sub y divided by the factor of safety, which is 2, and that computes to 184.8 kips. Considering buckling, the critical buckling load is pi squared EI over the effective length squared, which is equal to the length of the member because they're pin. Substituting numbers, pi squared 29,000 ksi, that's a comma, times the given I, 16.7 inches to the fourth, divided by the length, 10 feet, or 120 inches squared, and that computes to 331.6 kips. The F allowable based on buckling is P crit over 2 being the factor of safety. That computes to 165.8 kips. This is a maximum allowable force that can occur in the column, so the smaller value is going to control. That's this one right here. So we say F allowable equals 165.8 kips. You had to clearly indicate which of those two values controlled for full credit. It's also possible to take a stress-based approach. Rather than computing the forces, compute the allowable stresses and convert at the end. Start with the yield criteria. The yield stress, sigma y, is 42 ksi. The allowable stress is 42 divided by the factor of safety of 2, or 21 ksi. That's the yield criteria. Considering buckling, the critical buckling stress, computed as pi squared E divided by L over R squared, equals pi squared times 29,000 ksi divided by the slenderness ratio L over R. L is 120 inches, R is given as 1.37. Those are unitless. The ratio is unitless. Square that quantity and we get 37.3 KSI. The allowable stress based on that, sigma crit over 2, would be 18.6 KSI. Again, the smaller value controls, that's going to be this guy right here. To answer the problem, though, we need to convert this to a force. F allowable equals sigma allowable times A equals 18.6 KSI times the area 8.8 inches squared, and those numbers give you a value of 164 kips, which is a little bit different than the number we found using the other approach. Basically, difference is due to round off, not a big deal. Okay, so let's proceed to part B. Knowing that the allowable stress is allowable force in the member is 165.8 kips. In part B, we need to find the relationship between P and the force F in the members. If you proceed to try to find the reactions using the normal approach, and unless you assume the vertical reaction here is 0, you're going to run into a problem. The most efficient approach for this type of problem, which we hope you know by now, you have two members and a load. Just do a free body joint analysis on the joint connecting all the members. So that is our best approach here, free body diagram of joint B. I'll draw my joint. I have the force P pulling down. I'll assume all the members in tension, F1 and F2, like so. I'm going to start out sum of the forces in Y equal to 0 to find a relationship between F2 and P. I have negative P minus 4/5 times F2. I get 4/5 from the geometry of the triangle here. This is a 6, 8, 10 or 3, 4, 5 triangle. So the component of F2 in the Y direction is 4/5 of the total. Set that equal to 0. That tells me that F2 is equal to negative 5 force P. Negative value indicates it's in compression, the opposite of what I assumed. Or I can say that P is equal to 4/5 times the absolute value of F2, which would be the allowable force. So if I compute P from that criteria, P is equal to 4/5 times F allowable equals 4/5 times 165.8 kips. That's going to give me 132.6 kips. So that's one possible answer for the allowable load. However, I have to consider whether the member F2 is going to control or the member F1 is going to control. It might be possible for you to look at this and observe by inspection that the force in member 2 is larger than the force in member 1. But in order to be sure, we really want you to check both carefully on the exam. So next I will check some of the forces in X to find the relationship between P and F1. From some of the forces in X equal to 0, I have negative F1 plus 3/5 F2, that's the component of F2 in the X direction, equal to 0. I see that F1 is equal to 3/5 F2, or 3/5 times negative 5 force times P, or negative 3/4 times P. To invert that, I would say that P is equal to 4/3 times the absolute value of F1. Okay, now here is where I'm going to compare the two of these guys, 4/5 F2 or 4/3 F1. F1 and F2 both have the same allowable load. Okay, the smaller value of P is going to be the controlling value. P equal to 4/3 of F allowable, 4/3 of 165.8, is definitely larger than 4/5 times 168. So I can see this one does not control. At this point, I'm going to stop. The answer for this problem, the allowable load P, is 132.6 kips. And that completes this example.